I'm going to be going over doing molar conversions and the three definitions of the mole. So hopefully you've seen the mole before, but we have three specific definitions of the mole that we're going to be working on. The first one is that a mole is a unit that is equivalent to 6.02 times 10 to the 23 particles of whatever it is that we're talking about. So that is our first definition of the mole. So if I had a mole of donuts, that would just mean that I have 6.02 times 10 to the 23 donuts. So it's that many of whatever item it is that I am talking about. Now, the reason that we do moles in chemistry is because atoms are so teeny, teeny, tiny that it takes a whole lot of them to make up any sort of amount of measurable substance. So instead of saying that I have, I don't know, like 12 sextillion, that's not a real number, of oxygen molecules, instead you can say I have 2 moles of oxygen molecules. So a mole makes it easier to talk about the quantity of atoms or molecules that we have. The other definition sort of goes along with our gas law. So I'm going to skip down here to where it says at STP. So if you remember back to your gas laws, STP stands for standard temperature and pressure, and those are actual numbers. So your standard temperature is 0 degrees Celsius, and your standard pressure is 1 atm. So when you're at STP, 1 mole of any gas is 22.4 liters, or it takes up 22.4 liters of space. So that's our second definition of our gases. So that means that if I have 1 mole of O2 gas and that I'm at STP, that means that it will occupy 24 liters of space. So I have 24.4 liters of O2. And that's true for any gas. So if I have 1 mole of CO2 gas, I still have 22.4 liters of gas. So all gas particles take up about the same amount of space when you're at STP. That's what all those ideal gas laws were about. So this is one of our working definitions of the mole. So if I have 1 mole of any gas, it will occupy 22.4 liters of space. The last definition we're going to be using is about molar mass. So here is our last definition of the mole. So molar mass is equal to 1 mole of your substance in grams. So we'll be using the periodic table and looking at the atomic masses that are on the periodic table, and we're going to assume that that is the mass if we have 1 mole of that substance. So if you're looking at your periodic table, you'll see that oxygen has a mass of 16.00. Technically, 1 atom of oxygen is actually 16.00 AMU, atomic mass units, but we don't have a scale that is good enough in a lab setting that can measure the mass of a single atom. So what we do instead is we convert this into molar masses. So what we say instead is that 1 mole of oxygen is equivalent to 16.00 grams. So if I had a mole of oxygen, which remember is 6.02 times 10 to the 23 atoms of oxygen. So if I had that many atoms of oxygen, then it would weigh 16.00 grams. So if I'm looking at something like, let's do water. So if I want to know the molar mass of water, water's chemical formula is H2O. So it is made up of 2 hydrogen. So hydrogen has a mass of 1.01 grams. If I had 1 mole of hydrogen. Now, keep in mind I have 2 of them, right? So in this chemical formula, I have 2 hydrogen, and I've got 1 oxygen. So my total mass for H2O would be 18.02 grams if I had 1 mole of H2O. So we'll be using that definition of the mole as well. So if I have 1 mole of H2O, it would weigh 18.02 grams, which is actually very easy for me to mass out on a scale. So, and remember, that means that I have approximately 6.02 times 10 to the 23 molecules of H2O. That's about how many molecules I have to have of H2O in order for it to weigh 18.02 grams. So those are going to be our 3 working definitions of the mole. So the first one again is 1 mole is equivalent to 6.02 times 10 to the 23 particles. At STP, 1 mole of any gas will take up 22.4 liters of space. And the last one is that 1 mole of my substance in grams is going to be its molar mass. And I'll be using the atomic mass on the periodic table to figure out what those masses are. So you'll see I have a little map drawn on here. I call this my mole map. Our mole map is going to get quite a bit bigger, but I find this to be really helpful as I navigate from one unit to another. So back during quarter 1, you learned about something called dimensional analysis. It's the way that we move from one unit to another unit. Well, now we've got 3 units that we can move into. We can move into the mole, we can move into grams, we can move into liters. Oh, I lied, there's 4. Or you can move into particles. And by particles, we mean number of atoms or number of molecules. Particles is just a really generic term for that. So I can move into one of 4 units. So I'm going to use dimensional analysis. I'm going to show you some examples of how we're going to use that to convert from one unit to another. So I'm starting here with 3.6 moles of CO2, and the question is how many molecules of CO2 are present. So I'm at 3.6 moles of CO2. Now, what I know to be true about moles and molecules is that 1 mole is equal to 6.02 times 10 to the 23 molecules of whatever substance I'm talking about. In this case, it's going to be CO2. So if I'm using dimensional analysis, I know I want to get out of the unit of moles. So I want to get out of moles. So I'm going to put moles on the bottom so that that unit cancels. And I'm going to put molecules on the top of my conversion factor because that's the unit that I want to be in. So it'll be 3.6 moles of CO2 times 6.02 times 10 to the 23 molecules over 1 mole. And then when I go to solve this, what will happen is moles of CO2 will cancel, and when I multiply 3.6 times 6.02 times 10 to the 23, I will get the number of actual molecules in this particular sample. Now, if you take a look up here, I've included that in my mole map. So we're starting in moles, so this is where we started, and I'm asking you to go down to particles. So you're going to follow that down arrow, and you'll see that this is the conversion factor you should use, which is the same conversion factor that I used. So you can either know what the conversion factors are and then know which one goes on the bottom and which one goes on the top, or you can follow my mole map around and it will show you which conversion factors to use. So again, I'll show you that one more time. You started in moles. I know that because I see that my given value is in moles. And I'm asking you to move to molecules. Now remember, particles are molecules, or molecules are particles. So you're going to move from moles and you're going to go down. You're going to follow that down arrow to particles. And that down arrow is suggesting that this is the conversion factor that you need to use. Then you'll multiply it out and you'll get an answer. So let's see. 3.6 times 6.02 to the 23rd, and I got 2.6, oh, that's wrong, 2.2 molecules, nope, that's wrong too, 2.2 times 10 to the 24th molecules of CO2. All right, so let's try our next problem. So we're going to do a slightly different conversion factor using a different definition of the mole. So in this one, we are at 3.6 moles of CO2 again. We're at STP, and it's asking how many liters of CO2 gas are present. Now, again, we're going from moles to liters, and so the definition that we're using is that 1 mole of any gas, in this case CO2, is going to take up 22.4 liters of space if we're at STP, which we are. So I'll set up my conversion by starting with my given. So I'll write 3.6 moles of CO2. I'm going to use my conversion factor, and I want to get out of the unit of moles. So that is the value I'm going to put on the bottom. So 1 mole of CO2 is equivalent to 22.4 liters of CO2, and I want to be in liters, so I'm going to put liters on top. And then when I go to convert and do my math, moles of CO2 cancel, because moles divided by moles cancels. And then I'm going to be left in liters of CO2. So it'll be 3.6 times 22.4 liters, and I got 81 liters of CO2. Now, if you're wanting to use the mole map from above, again, in this particular problem, we started in the unit of moles, and I asked you to go to volume. So then you're going to follow that arrow up to volume, and you're going to see that this is the conversion factor that you're going to use, which is the same conversion factor that I used. All right, so we've got 2 more problems that I wanted to show you so you can see how you should be approaching these problems. For our next one, we've got 3.6 moles of CO2 and how many grams of CO2 are present. So again, 3.6 moles of CO2 is what I'm starting with. And then I'm going to have to multiply it by some conversion factor. And I want to get out of moles, and I want to be in grams. So I'm going to go back up and look at this definition of the mole. And I'm going to remember that my molar mass, or 1 mole of CO2, is equivalent to its molar mass in grams. Now remember that molar mass you get from the periodic table. So I'm going to go to the periodic table and I'm going to look up carbon, and I see that 1 carbon has a mass of 12.00 grams, and that each oxygen has a mass of 16 grams. And I'm going to add all of those together. That was carbon. These are each an oxygen. So when I add those all together, I get, hold on one second, 44.00 grams of CO2. So 1 mole of CO2 is 44.0 grams of CO2. Now I can use this as a conversion factor in my actual problem. So I want to get out of moles. So I'm going to put moles on the bottom, and I know that 1 mole of CO2 is equivalent to 44.00 grams of CO2. I want to be in grams because that's what I've asked you to move into. Moles will end up canceling, and then when I solve it across using math, I will get my answer in grams. And I got 158.4. I think I only get 2 sig figs. So 158 grams of CO2 is actually going to round to 160 grams of CO2. And that's just sig figs, 2 sig figs. So if you have a question about sig figs, I can help you more with that in class. All right. Again, if you want to follow the mole map up here, I've started in moles. I've asked you to go to mass, which is in grams. And so this is the conversion factor you're going to have to use. Now keep in mind, you're going to have to figure out what that molar mass is by using the periodic table. All right, last one. This one is a two-stepper, so I just want to show you how to do that. I'm in molecules of CO2, and I'm asking you to go to grams of CO2. Now, I don't have a conversion factor that goes from molecules to grams. I have molecules to moles. I have moles to grams. So in this case, I'm going to have to do 2 steps in order to get my conversion all the way over to grams. So I always start by writing my given, 9.68 times 10 to the 24th molecules of CO2. And I remember that my definition for the mole is that 1 mole of anything, so 1 mole of CO2 is equivalent to 6.02 times 10 to the 23 molecules of CO2. And so I'll use this as my conversion factor. I want to get out of molecules, so molecules will have to go on the bottom. So 6.02 times 10 to the 23 molecules of CO2. And then I want to be in moles. Well, I want to get out of molecules, so I have to get into moles. So mole will end up on top. When I multiply these, molecules will cancel, and whatever answer I have will be left in moles. The problem is I don't want to be in moles, I want to be in grams. And I already did the work above, and I remember that 1 mole of CO2 was equivalent to 44.00 grams of CO2. Well, I want to get out of moles and I want to be in grams. So if I want to get out of moles, that means that this time I will put moles on the bottom, so that it'll be moles divided by moles. So 1 mole of CO2 is 44.0 grams of CO2. And then moles of CO2 will cancel, and then when I multiply all the way across, my answer will now be in grams of CO2. So in my calculator, I'll put 9.68 times 10 to the 24th. I'll divide that by 6.02 times 10 to the 23rd. And then I'll multiply that number by 44, which gives me an answer of 706 grams of CO2. And I get 3 sig figs because of this number over here, and I already have 3 sig figs, so this is the answer. 706 708 grams of CO2 is what I got in my calculator. All right, so that's how you're going to use these definitions of the mole in order to convert from one unit to another. If you wanted to use the mole map for a problem like that, you could scroll above and you will see that you have started your mole map in particles, right? Molecules are a type of particle. So you have started down here in particles. I've asked you to go to grams, which is mass. So that means that you have to follow this arrow up to moles. So you're going to have to use this conversion factor, which I did. And then once you're here, you would use this conversion factor over to mass, and that looks like this, and you'll notice that is the second conversion factor I used. So I use those same conversion factors when doing my work as well. We'll do a lot of practice in class, and then feel free to ask me any questions that you might have.